Thank you everyone for joining us today. The webinar will be beginning soon. We'll be getting started in just a moment, but I would love to tell you about some upcoming events in the meantime. On Wednesday, June 17th, we've partnered with the University of Michigan Center for Occupational Health and Safety Engineering to offer a free webinar, Considerations in Exoskeletons Human Factors, with Dr. Leah Sterling as a part of our Education and Research Center Ergonomics webinar series. We'll also be having Macroergonomics, a systems approach to human factors in ergonomics, an 8-week online course beginning on July 13th with Dr. Michelle Robertson. Our next industrial hygiene webinar will be on August 11th with Dr. Brian Pavlonis on nail salon exposure assessment in partnership with New York, New Jersey Occupational Safety and Health Center. To learn more about these events, you can visit us at coeh@berkeley.edu/aboutce. On behalf of education and research centers throughout the country, we're pleased to present the 2020 Industrial Hygiene Webinar Series, offering free webinars the second Tuesday of each month. This collaborative effort on behalf of each ERC's continuing education program aspires to provide access to current research supported through NIOSH ERC programs. Thank you so much for joining us today. Today's webinar, Exposure Assessment for Epidemiology Research, Use of Routine Industrial Monitoring Data, is brought to you by the Center for Occupational and Environmental Health, Northern California ERC, Dr. Katharine Hammond, and Dr. Elizabeth Noth. A few housekeeping items first. You will be muted during this presentation. If you would like to ask a question, please enter it into the online Q&A. We'll save time at the end of the presentation to address questions. All participants who logged in with their registration email for the full live presentation today will receive a link to the recording and an evaluation form tomorrow around 12 p.m. Pacific. This evaluation will qualify participants for a certificate of completion worth 1 continuing education contact hour. Once completed, you'll be able to access your certificate. This presentation is being recorded and will be made available on the COEH Northern California YouTube page and on our website. At this time, we're pleased to welcome our presenters. Dr. Katharine Hammond is Director of the Industrial Hygiene Program and Professor of Environmental Health Sciences at the University of California, Berkeley School of Public Health. Her research career has focused on assessing exposure for occupational and environmental epidemiologic studies, including metalworking fluids, diesel exhaust, light metal manufacturing, solvents, welding, and chemical, physical, and ergonomic exposures in the semiconductor industry. Her expertise in chemistry, industrial hygiene, risk assessment, and public health enable her to develop innovative methods to characterize air contaminants and to create models to evaluate exposure for epidemiologic studies. Dr. Elizabeth Noth is researcher in environmental and occupational exposure science and is primarily focused on assessing air pollution exposure for epidemiologic studies. She is trained in exposure assessment, modeling, and spatial analysis, with a focus on modeling short-term air pollution exposures. Her current research includes exposure assessment method development for environmental and occupational cohorts, evaluation of polycyclic aromatic exposures, and the role of biomass burning in ambient air pollution exposures. Thank you both so much for joining us today.
Thank you, Michelle, and Dr. Noth and I both thank you for the introduction and thank all of the participants for joining us today. Today I want to talk, in the next slide please, about how we can use, what are job exposure matrices, how these use the routine data that are collected, and on how the long-term averages can be affected. How the long-term averages can be affected by engineering controls, workplace processes. Okay, I'm noticing, is this any better? Can somebody let me know, since I'm getting messages that people can't hear me? Yes, okay. All right, so we'll be talking about how various factors can change exposures through the time, and how we can look at this and use job exposure matrices in these. In particular, I want to talk about the effect of misclassification in epidemiology studies, and in particular, exposure misclassifications. Next slide, please. And next slide, please. So if we imagine we have a population of people who were controlled at work, and the disease rate among those people per 1,000 workers is 10, the light blue bar. And we look at people, the comparison group of people not exposed, and their background disease rate is 2. There is some background rate. We have a relative risk of, in the numerator, 10 out of 1,000 of the workers, and in the denominator, 2 out of 1,000 of the people not exposed. Then the relative risk is 5. There's a 5-fold increase in disease among those who are exposed at work. This is the truth. Now imagine that we have a little misclassification, and some of the people who are exposed are classified as unexposed, and some of the people who are unexposed are classified as exposed. In that case, we see something quite different. The blue bar goes down because some of those people with disease have moved into the other category, and raising the orange bar. All right, so now the relative risk is, for instance, 8 out of 1,000 for those exposed, and 4 out of 1,000 for those not exposed, and the relative risk can be reduced to 2. So clearly, this has several effects. What that means is that, first of all, the apparent relative risk is much less. Instead of being a 5-fold increase risk, there's a 2-fold increase risk. And this may reduce it sufficiently that given the confidence interval of the value, it may become no longer statistically significant. So let's take an example now of 100 people who were exposed and 100 who were unexposed. And again, let us say that in truth, of the 20 of those who are exposed have a disease, and of those who are unexposed, 2 aren't. So the relative risk in this case is 10. And now imagine that we have a 10%, a very small rate of misclassification. So of those 20 people who were exposed and had disease, 2 of them, 10%, end up two of them end up showing not being included in that category, and they move over to the exposed, we -2 and +2. And the same for those who are not diseased, we get that problem. So now the relative risk goes from, was originally in true, it's 10, but the observed becomes 4.5. So we have exactly the same kind of problem that we were talking about. So moving to may take a minute now. I'm seeing messages that people are having trouble with the audio. Is that still a problem? Okay. Okay, so moving to the next slide, please. I want to talk about a study that was done quite a while ago, but I think is quite illustrative. And this was a question of steelworkers. And the union there asked researchers at the University of Pittsburgh to do an epidemiology study in their plants. So there were 7 plants. And if you look at the observed versus compared to the expected rate of death, SMR for those of you who know that, the rate was 82. So they had 82% as many observed cases as you would expect, less. This is known as a healthy worker effect. And some people at that point might walk away and say, oh, there's no problem, among steel workers. But if we break it down and don't group all steel workers together, and instead look at a series of them, and we look at them in different locations, what we see is that if we, instead of comparing them to the general population to get away from the healthy worker effect, what we see is that for instance, in the general labor group, we have a little more than a little higher rate of death. It's not stunning, but it's still very useful. We know maybe it's real, maybe it's not, but it's a little bit higher in some of these selected jobs. And if we look at the cancer rates, again, we would see that overall, next slide, please, that the cancer rates are about equal across all of them, with a small increase in the coke plant. And again, one might say, let's not bother to look, but let us look. Let us look a little deeper into the coke plant and see what we actually see. So for those of you who don't know, a coke plant is a really, really dirty, dirty job. And so if we take the coke plant and we look at the oven, this is a picture of someone working at the oven. There are some pretty horrendous fumes coming out from heating the coal or the petroleum coke up, and to drive out all the bad gases and vapors in there, which of course go into the air. And what we notice here is that those who work in the oven have a 70% higher rate of cancer than other steel workers in other parts of the plant. But if we talk about topside, where the fumes are really coming off, first of all, I guess the lung cancer rate is about 3 times higher for those who work in the oven. And then a topside, we get over 1,000-fold increase. So moving on, and I want to give another example. This is from our study of spontaneous abortion among people in the semiconductor industry. And in this case, we're looking at those who worked in the wafer fabricating clean rooms, or fabs, compared to those who weren't. And there was a 43% increased risk of a spontaneous abortion among the fab workers. If we, however, became more specific in defining the exposure to which these people were experienced, and we had several work groups, the work group of photolithography, we see there's a 67% increased risk. Now, if we move further and go to looking at some specific exposures, next slide, please. We look at photoresist solvents. What we can see is if at different levels of exposure, level 1 is exposed at the lowest level and 3 at the highest, we see an actual dose response happening here. And the level 3 has almost a 3-fold increased risk. So the point here is the more specific you can get to the causative agent, which you may not know when you're doing your study, the better you can do it. So these are just a couple of examples of how either exposure misclassification or just not having it as precise as possible can really make dramatic changes in the observed relative risks that we're looking at. So moving to the next slide, we often hear in epidemiology people talk about confounding as the big problem in epidemiology, but an epidemiologist from I have a great deal of respect, Aaron BLAIR at the National Cancer Institute wrote that 2 of the major methodological issues raised in epidemiologic studies of occupational exposures are confounding and misclassification. But he says exposure misclassification is of a far greater concern. Non-differential misclassification generally leads to bias of the relative risks towards the null, and the magnitude from relatively small amounts of misclassification can be sufficient to lead to an interpretation of no effect, a misinterpretation. Furthermore, next slide, please. He goes on to say, thus, interpretation of epidemiologic data and evaluations of epidemiologic studies should be more concerned about exposure assessment than confounding. But we find this is not generally the case. So much more attention goes into things that have a smaller effect. So today we will be talking about these effects, and what I want to do is talk about exposure assessment. And first of all, I think it's important to realize that we have many different reasons for which we do exposure assessment. Within industry, most often, it's likely to be compliance with standards. So these could be OSHA standards or Cal-OSHA standards, and these can be airborne concentrations or biologic exposure assessments. And when doing that type of exposure assessment, if you're working for the company, what you want to do is you want to find the person you think has the highest exposure and measure that. And if that's within the standards or your goals, then you can feel fairly sure that others are well protected. Now, if we move to risk assessment, exposure assessment's used for that as well. And it's used in two different aspects of risk assessment. The first being in the dose response, where you actually look at how either whether in animals can be dose response or in people, the rate of disease at differing exposure concentrations to establish the potency of a particular agent. And then the second step is in the risk management, trying to understand how much of the population is exposed at those levels and how to control those. And then moving, however, today we're going to talk about exposure assessment for epidemiologic studies. And this is really something that's quite different. And here, for all exposure assessment is in fact intensity times duration. Intensity is how much, how intense is it, what is the concentration, and durations for how long. Is this a 15-minute exposure, a brief exposure? Is it an all-day average exposure? All of those are important issues in examining all of this. But in epidemiologic studies, we need to look at this a little differently. In this case, we do need to think about things like what kind of health effect are we looking at? Are we looking at an acute effect, such as suddenly, having your eyes irritated or your throat irritated? Then it may be an effect that happens in just the moments before, and it can be a very short exposure that leads to that. Or it could be an exposure that happens through a day or two, and then, over the week, you progressively have more and more difficulty breathing. Or it could be a chronic health effect that happens, such as cancer, that happens from years of exposure. So you have to identify what you think that type of mechanism is. And also then whether it's the acute or the chronic exposure that's important. We need to understand the biology, the data, what data are available, such as job titles, sampling data, job histories, production rates, changes in engineering controls, environmental monitoring, and what resources are available to do this. Harvey Checkaway, an occupational epidemiologist, has actually written a hierarchy of exposure classifications for occupational epidemiology. And the crudest of all is, ever versus never employed in industry. For instance, did you work in the chocolate factory or did you work in the dry cleaning industry type of thing? Or a little bit of a refinement would be the number of years that you worked in the industry. One could do job categories by process or task. And that was, for instance, the work group where I said photolithography had the higher rate than other jobs. Or job categories ordered by exposure intensity, quantitative exposure intensity categories, and quantitative dose categories, which is what we're going to talk about next. So to do that, we often develop what are called job exposure matrices.
Hey everyone, thank you, Kathy. This is Betsy speaking now. I'm going to discuss job exposure matrices, or JEMs, how they're built and how they're applied. So a job exposure matrix is exactly what it sounds like. It's a table of jobs with an exposure for each job. A JEM can be constructed for different types of exposures, for example, respiratory, dermal, auditory, physical demand or intensity, even psychosocial stress. JEMs can be used for more than one purpose as well. However, the primary purpose that we're focused on today is to enable the estimates of dose response effects in epidemiology studies. This table on the right shows a very simple JEM taken from my initial work in the American manufacturing cohort. It shows just a job group name and a single time invariant concentration for total particulate matter. Here's a more complex example from 1986 publication titled Estimating the Relationship Between Exposure to Tar Volatiles and the Incidence of Bladder Cancer in Aluminum Smelter Workers. The first column shows the jobs organized by where they're performed within the facility. In the remaining columns, there are exposures calculated for each job during each time period across the top for benzene soluble matter concentrations. So this GEM has added in time varying data. This can be very important to account for in epidemiology research. And Kathy's going to talk about another example here.
This is from some of our work with looking at metalworking fluid exposures and a series of papers that we have on the health effects associated with that. One of the things that one can find, and this is actually using the data from the companies, and this is trying to use the routine data, is that over the decades, we can see that, for instance, if we look at the grinding operation and straight metalworking fluids, this is highlighted in the first red rectangle, the arithmetic mean concentration was 18 milligrams per cubic meter in the 50s and 60s, and that was decreased, guess what happened around 1970, to 3 milligrams per cubic meter, and then by the 80s down to 2, a little further.
Okay. And here's another example of a job exposure matrix. This one is based on survey data. The question up at the top here, what level of static strength is needed to perform your current job, is the survey question. And then the GEM took those questions, the numerical value, and averaged them. And so for each job title, and so it shows here the mean score on the survey. So as I mentioned during the examples, GEMs can come in many types. The simplest type is probably an ever-never qualitative GEM. And the next up in terms of complexity, if you have more data, is an ordinal or semi-qualitative GEM. This is a GEM where you have some information and could assign, for example, a high, medium, low category for each job using data or expert judgment. And last, the highest resolution data would be a quantitative GEM based on measurement data. And so where do we get data on to make these GEMs? So a first example Kathy's going to show.
We can look at safety data sheets and company quality control records. And for instance, what's contained in something, and we might just have a yes, no. So this is just a synthetic example of saying with 3 different metalworking fluids, some of them have chlorine compounds, some have sulfur compounds, some have biocides, some have nitrosamines, and some have nitrates. This then can be also used for this becomes like an ever-never type of analysis.
And so if we're looking at sources of exposure data for GEMs that are quantitative, there's sort of a limited list. The first is the best case many times would be if you could go into the workplace, conduct exactly the type of sampling you want to build your GEM, and just have the perfect data set. But aside from having access to a workplace, adequate funding to do all that sampling, no need to time travel to collect historic samples, and that a small enough project that you can characterize it and all of that is pretty rare. So the general approach is to use, if you can. Oh, and also I wanted to say that the challenge of getting access to the workplace for those who are considering it should not be underestimated. It's a significant hurdle for research to go forward, larger probably than even getting funding. So you want to be sure that you've got that in hand. So if all of that is too much of a challenge, then the next available source is often company-based data sets. And so if you're conducting a research study on a given industry or workplace, it's likely that you have some idea of what the exposures are that you're worried about that are going on there. So companies are required by OSHA to collect data on certain hazards in order to prove that they're providing adequate protection for their workers. Excuse me, for example, employers must characterize the nature and magnitude of employee exposures to respiratory hazards before selecting respiratory protection equipment. This often requires sampling. So sampling required for this is either worst case scenario or routine monitoring data that's representative of enough shifts and operations to determine the full range of exposure for those workers. And so what is the minimum exposure data we need to be able to use data collected by others? Kathy's going to go over this.
So one of the things that happens is at one point, you know, the data that are there just we collected these are our benzene samples and they're not useful. So how do we make sure that they're useful? Some of the things that we need to know is where was the sample taken? You know, is it a personal sample or an area sample? And what is that person doing? What's their job title? Which plant are they in? Which process are they near? And second is the duration of the sample. Is the sample a 15-minute sample, a task-based sample? Is it a full shift or near full shift sample of 8 to 10 hours? What measurement method was used? Because that may require, if we're mixing measurement methods and sampling methods, then we may need to make some adjustments to compare in different time periods. The purpose of the sampling is very important. Is the sampling happening because there was a spill and they're worried about how high the exposures were, or is it a typical and routine sample? If we do have an area sample, is there any way we can use that to relate to personal samples? And also we finally need to know the limits of detection for our samples. Next slide, please. And then this is an example of where there can be some diversity of sampling and analytical data. So this was in our metalworking fluids study, where it turns out that in the earlier years, electrostatic precipitators were used to collect the samples, and later they were filter-based samples. And similarly, different analytical methods were used, sometimes gravimetric and sometimes infrared. And that has to be taken account of in doing the analyses. Also, we're concerned about, we may want to know about the effect of engineering controls on exposures. And so it's useful sometimes to gather data, especially useful if companies have collected data before and after an engineering control was introduced. So if we look at grinding, we can see that if enclosures and local exhaust are used, that before the controls, the arithmetic mean was almost 7, and that was reduced to about 2 after the controls. So the ratio was a 5-fold reduction. And just for information, if we just put general air cleaners in, and that was actually tried, there was a very small reduction from 5 to about 3.5. So these are just some of the ways in which we can look at that. Betsy?
Oh, Betsy, I think you are still muted.
My goodness, I'm so sorry, you guys. We've discussed different types of GEMs and the types of data we can use to build them. However, we haven't talked about how they become a worker exposure for epidemiology. So conceptually, we combine the GEM with the worker's job history. So the GEM here is on the left and the job history is on the right. And here in this example for lucky worker A, who worked at the llama farm for 5 years. So if we combine these two tables, we make a full exposure history for worker A. In this case, the GEM was time invariant, which is so it didn't change over time. But as worker A changed jobs, their exposure also changed. So you can see that the GEM has been used to calculate both cumulative exposure from 2004 to 2008 and exposure to the previous year, exposure in the previous year. But there are other exposures you could imagine that you might want to calculate from this exposure history, depending on your research question. So this is a schematic showing those linkages. In our simple llama farm example, we had measurements available for each job of interest. This is rare. Generally, there are a significant number of jobs that have no measurements. So what do we do? We group similar jobs together to assign exposures to job groups rather than to individual jobs. One popular way is to convene a panel of experts, such as these pictured, who are comprised generally of workers, industrial hygienists, and academics, to discuss the most logical way to combine the jobs. For example, you might have a whole bunch of alpacas on the llama farm. Since alpacas and llamas have similar care requirements regarding feeding or environment cleaning, this is according to both the workers and the industrial hygienists, you could combine those into a standardized job of llama and alpaca tenders. Another common way, if an expert panel isn't feasible, is to use job titles to combine. For example, you might have two llama farms, one that was sampled and one that wasn't. It might be reasonable to assume that all the llama tenders at both farms perform the same job, and that you can combine them into one group using data from one farm for the other set of workers as well. Kathy's going to give a slightly more realistic example.
So in an epidemiologic study we did looking at whether or not diesel exhaust causes lung cancer, we examined railroad workers' exposure. And we had two epidemiologic studies, a cohort study with over 55,000 workers and a case control study with another 3,600 workers. Obviously, we couldn't do individual personal sampling on all these workers, and many of them had died. So in fact, what we did is we used the Interstate Commerce Commission had actually reduced thousands of different job titles already to 155 job codes, but that was too many as well. We chose 39 of those job codes as being those that for which we could actually know for sure that they were exposed to diesel or not. Some of the job codes often have few people in them. And of those 39 job codes, we reduced those further to 13 different job groups for which we did exposure characterization. And in this case, we're not using company data, we did our own sampling. And in the next slide, what I do is show you the 39 different jobs are kind of laid out. So for instance, we had 5 different career groups which were useful in the analysis at one point. And there were clerks and station agents who had no diesel exhaust exposure. And these are some of the titles for the 10 job codes there. Signal maintainers had very low diesel exposure, and there were 6 different job codes, whereas for engineers and firers, there were 8 different job codes. I've listed some of those. Similarly, breakers and conductors were a different group, and then there were 12 job codes and 6 job codes for the repair shop workers.
Okay, so there are also some, just to sort of sum up, like there's the common challenges when you're building a GEM or applying it, are gaps in the exposure data, and the way that you can deal with that is to either model the data, or occasionally you might simulate tasks in the lab and measure them, or if you can, go out and measure them in the field. And then in gaps in job histories, which we're not really going to go into during this talk, you have some that are real from unemployment, and then others that are database errors. And so now I'm going to talk about a case study of building a GEM using company collected industrial hygiene monitoring data. And this is in the American Manufacturing Cohort, the AMC. The epidemiology study the initial one was to evaluate the relationship between incident ischemic heart disease and both cumulative and recent particulate matter exposure. So the health data started in 1998. The job history information was easily available from 1996 onward, and we had company industrial hygiene sampling data from 1980 onward electronically. So the first step, at the 12 facilities in the study, there were over 17,000 total particulate matter, or TPM, samples in the database. But our first step was to exclude the area samples because we only wanted to use personal monitoring data. So this brought the number down to around 12,000. Then we limited our personal samples to only those collected to represent daily routine activities. In doing this, we excluded samples collected as worst case scenario samples and those collected for a specific project called diagnostic sampling by the company. Diagnostic sampling also included samples collected by employee request and during unusual or infrequent tasks. This reduced our samples to a little below 10,000. Last, we limited our final data set to full shift samples only, defined by us to be greater than or equal to 70% of the shift length. This brought the final count to 8,385 TPM samples at the 12 facilities. And I just want to sort of put a little note here to say that we were extremely lucky that we were able to focus like this, and that there might be other times when you would want to use some of those data if you were desperate. So for our initial GEM, we calculated a mean for each unique combination of facility, department, and job title. We did this for every job we knew about, which was every job that had a TPM sample. Next, we combined this GEM with the job history data. Following the familiar diagram, we went to combine our unique jobs on the IH database side, which is on the left side here, with our job history information, which we'd gotten from AMC human resources databases. It was a huge fail. The jobs on the IH side were not standardized to the jobs in the HR database. The HR database had different codes in the job titles and sometimes had inadequate data to match, different types of abbreviations, etc. So we decided to group job titles into distinct exposure groups in order to match to HR. So in a previous study on noise exposure in the AMC, researchers and the company had convened a panel of experts to form unique job titles in the IH database into distinct exposure groups, or DEGs, that reflected similar types of work and processes. They were not specific by agent of exposure. These experts were current and former employees, industrial hygienists, and academics. The HR job titles were also assigned to the same DEGs once the DEGs were formed. So now we went back and, this resulted in forming 294 DEGs. And these DEGs were unique to each facility, and each facility had its own system of naming jobs. So there were some DEGs that had very few jobs and others with 10 to 20 jobs. Basically your classic splitters versus lumpers occurred in all of this. You could see that. And so then we went back to and linked by DEG, and boom, it matched. And we were very happy, except the DEGs in HR that didn't have any measurement data and thus didn't have a value in the GEM. So we had 294 DEGs total that we needed to assign an exposure to, and only 210 had measurement data. So this table shows that what we did to, it shows 71% of our DEGs were covered, which accounted for 85% of the total job years in the cohort. The most common approach we used to fill the missing data in the GEM was to use values from other facilities. We had a few DEGs that used other methods, such as using a respirable PM sample, but these were relatively uncommon. In the end, about 8% of the cohort received a default value. And just to note here that it's important when filling holes in your GEM to be aware of how many people are in each DEG, because you don't want to spend 2 weeks or 3 weeks trying to get a value for a DEG that only has one person year in it. It's just not worth it. So you focus on the ones that have a lot of people in it, and then you know how far to go until you need to just move forward. And so this just shows a little example of how the various DEGs, which are called SCs in here, overlapped at different facilities, thus allowing us to model data. So you can see across the top that the facilities are given by letter, and the DEGs are listed on the left under the SCs title. And so you can see, for example, in the middle, the hot mill operator and the cold mill operator are sort of paired at both in fabrication at facility A, E, and G. And so that is a natural, you can see from things like that they're similar facilities and conducted similar kinds of work. And so we were able to model from one facility to the other when those types of relationships were present. Okay, so now that we had the basic structure of the GEM and the matching job history, we expanded on the information and the complexity of the GEM. First, we added PM 2.5 exposure using the relationship between simultaneously collected PM 2.5 and PM TPM measurements on a subset of workers. We made a new gem that was the percent of TPM that is PM 2.5 by DEG. Then we combined this gem with the TPM gem to get a new gem that was PM 2.5. And then we accounted for known workplace changes. In the IH database, the company had recorded when various changes took place in engineering controls, processes, materials, shift length changes, and tasks within jobs, either starting or stopping or switching to another job. We defined intervals between workplace changes within each job tested for statistically significant differences between the two time periods. When the jobs were statistically significant, we separated them into new time-dependent jobs. So this example shows one job, one DEG, the pot room tapper, and the pot room tapper had 3 distinct periods of working exposures. Before February 1987, between February 1987 and January 1989, and after January 1989. So you can see in the graph that those are 3 really different periods, and that if you were to assign all of the exposure to a worker after 1989 to the concentration in the 1987 job, you would really create a lot of exposure misclassification. We also added respirator adjustment. The company had collected respirator use information with every single sample, even if only to record that it was not used. And we used these data to adjust individual samples for 2 protection factors. One, the OSHA respirator protection factor, which assumes perfect fit and perfect compliance. And second, a workplace protection factor that assumed a realistic fit and compliance level. And so then to put these together, how did the 2 different adjustments to the particulate matter GEMs work? You can see across the top is respirator use, and across the side is workplace changes. The top bank is changes within the percents of DEGs, and the bottom is percents of person years. And you can see it's a slightly different story. On the top part, you can see that 41% of the DEGs in the GEM used either respirator adjustments or workplace changes, or 13% used both. Whereas in the bottom part, in person years, it's a much fewer people had no adjustments. So 60% of the exposure assessment by cohort person years used either a respirator adjustment, or workplace changes, or both, 28%. So over twice as many people when you look at it by person years instead of by DEGs. And so the result in all of this was that we ended up with 12 different particulate matter GEMs, and they're all useful for one reason or another. And of particular interest from an IH perspective is to take 2 of these GEMs or 3 of these GEMs and say, well, what happened as we moved from a time invariant GEM to a time varying GEM? Like, how much did our exposure assessment become more precise, or what happened with the relative risks and hazard ratios? Were they improved? Was the precision improved? So having multiple GEMs is a positive. And now Kathy will give some concluding remarks.
So in doing some of this work, it's important to recall your research question. What is it you're looking at? For instance, if we're in the AMC cohort, one of our research questions was, were there more heart attacks among workers with higher particulate matter exposures? And for that, we had 2 different biologic ways to think about it. One is to look at chronic exposures accumulated through the working lifetime, and the other is to examine what was the most recent exposure during that particular year. And by setting up the GEMs in the way that we're talking about, one can either have recent or cumulative exposures. Now, again, to remind you, there are these various pieces of information that are important. For those of you who work for companies and are collecting routine data, I strongly encourage that each sample you take includes some of this information. Should also include if respirators are used, or if there are other unusual circumstances, places for comments. And for those who are using the data, it's very important to be careful to look at the data and make sure that it fulfills the appropriate thing you're looking for. So if you're looking for routine exposures, make sure the samples reflect that and not lack of routine samples. Betsy? I want to thank you all for attending. I apologize.
And that's all. Thank you, Kathy. Thank you, everyone.
Great. Well, thank you guys both so much for this presentation. We do have some questions that are coming in through the Q&A. We'll start with the first, right up at the top here. Are the company supplied data somehow masked so that companies cannot skew data to prevent citations and fines?
I am a little unclear on the question, but let me answer two ways I can interpret it. We always report our data, as you will have noticed here, as company A or facility A, B, C, D, or sometimes 1, 2, 3, 4. But the point is we don't identify where these are coming from. Our goal is not to be doing inspections. And now, on the other hand, the question is the company data collected honestly? I happen to believe that generally speaking it is, but there are ways in which one can kind of look for that and see. There's, of course, a classic case that Noah Satius identified that a lot of coal miner companies had actually, he found aberrations in the data and which led him to inspections and looking at the samples and realized they'd literally taken air hoses and blown dust off of the filters prior to weighing. So, I mean, yes, there can be that kind of skewing, but I don't think that that's common. I hope that that answers that question.
Thank you. Are there any exposure assessment interferences that can be determined when routine sampling only includes colorimetric, PID, other point in time measurements?
This is a more complicated question because it relates to the looking at the sampling method, which is a little bit outside the talk. I'll briefly talk about this. Some of this relates to how well you know your environment where you're sampling. So if you're going to use, for instance, PID, photoionization detectors, or other real-time samplers, it's always important to understand the basis upon which the detector is operating and what interferences are known, and then to know whether those are present in your particular workplace.
Thank you. And we also have some questions regarding the DEGs. Is there a minimum number of people that should make up a DEG, or conversely, a maximum number of people? And someone was also wondering how long it can take to assign DEGs.
Oh, I guess I'll start with I'll try the easier one, which is that when assigning DEGs, we tend to assign them starting on the job end. So it's not about the number of cohort person years that are present in a job. That is, I mentioned that as a way to decide about if you don't know something, how to prioritize working on it. But generally you start with all of the information from the workplace to then categorize and group together into DEGs. And then the second part of how long does it take sounds sort of like a trick question or some sort of plant. It can take forever. It can take a long time, or it can be very quick. It sort of depends on whether you're a splitter or a lumper and what the purpose of your epidemiology study is. So it's sort of one of those with a balanced approach. It takes it's a reasonable chunk of your research time on a given project, but it's not insurmountable, nor is it terrible. But if you decide that you have to get everything perfect, you'll end up spending a lot more time on it.
Thank you. We have another question. What kind of exposure agents do you measure for llama workers?
I don't know if that is a joke.
Allergens.
Well, are they joking? I did imagine what they could be measuring. We'll say they're measuring either llama allergens or endotoxin And if it was not a serious question, then they were measuring how happy, the happiness quotient.
Thank you both. We do have time for some more questions, so please, again, feel free to enter any questions into that online Q&A box. We do have a question that it's a little bit off topic, but I think you guys might have an answer to it. Oh, and we say it was a serious question.
Well, you could measure a lot of things. That was a fake study, but it would be a fun one to do. If I were a llama tender, I would worry about my endotoxin exposure, I think. What would you worry about, Kathy?
I think that's probably good. Maybe solar exposure and UV radiation.
Yeah, that's true. Heat illness.
Thank you. Good answers to the serious question. And we have somebody who is asking, they have a crossing guard that's claiming idiopathic pulmonary fibrosis. They're in that capacity for no more than 30 minutes per day, and they're wondering what tests or information they should be using to see about traffic exhaust in the area.
I'm going to start, and I'm going to then let Betsy answer more on that. But first of all, this again is outside of this talk, and it's an example. But we'll go ahead and talk about it. I want to make it clear, though, this is not an epidemiology study. This becomes an industrial hygiene. Like, let's look into what are the possible exposures, and it's a good question for that. But at the moment, we're not thinking of doing an epidemiology study on such a rare disease unless, it would be more likely a case control study than a cohort study unless 3 cases of that showed up among crossing guards. So Betsy, do you want to talk about what traffic exposures you could think of?
Yeah, and I've actually done, yeah. I mean, I think that when you're thinking about an illness, sort of to take this into the context of the talk a little more, with idiopathic pulmonary fibrosis, it's not a sudden onset type of thing. And so you'd want to think, how much time do I want to be looking at in my GEM? And when I'm looking at these people, at what tests, with traffic exhaust, you could do a lot of different things from measurements to just, size of road. But yeah, I think as it pertains to this talk, I would say that you would really want to know more about your illness and what the research question is before you went out and started monitoring agents.
And I would think about, one could think about agents such as perhaps asbestos fibers or tire wear materials that might be causing that. But that's really a very challenging kind of situation when you have an outcome like that.
It is, and I actually have done some work on idiopathic pulmonary fibrosis, and I know that there's very, very, very little out there about what environmental determinants might increase one's risk of developing idiopathic pulmonary fibrosis. So that's another sort of gap in knowledge that's going to be hard to overcome. So I think a lot of research, a lot of literature review would be recommended before you started in on that.
Thank you both so much. We have another question about, are AIHA SEGs sufficiently detailed for DEGs?
So we're talking about similar exposure groups and designated exposure groups, is that right? That's for DEGs?
Yeah.
Yeah, so similar, they are, conceptually they're very similar. A similar exposure group, though, is not a set thing. It's something that in my own research, we actually would develop it in a particular setting. But the concept of SEGs is quite comparable to the designated exposure groups. In the particular setting here, the exposure database actually defines SEGs for their place, and every time they put a new engineering control in or change the process in any way, they would, even though the job title was the same and the people were doing the same things, it would become a new SEG. We just sometimes could not have a separate SEG for everything. And so we actually combine some of the SEGs into DEGs. Do you want to say more about that, Betsy?
Yeah, I mean, I'm not super familiar with the AIHA SEGs, but I think that one one difference between certainly how the company used segs and how I've often seen it used and the DEGs we used is that segs usually include a grouping by all of the above plus the agent of exposure. And so you'd end up with a different seg for, say, noise than total particulate matter. In our work, because the company and the initial researchers were more, wanted to be more inclusive and be able to match for many different studies, they actually made the DEGs, which we called distinct, because they're not agent specific. And so we didn't want it to sound like we were referencing the similar exposure group sort of that is often referenced in the literature. We wanted to sort of be our own thing so that people would notice, oh wait, I don't know what this is, and read more carefully to see that it doesn't include agent when we assign and group.
And so in a job exposure matrix, one could have jobs, which is the literal translation, but more commonly there's more grouping, and then instead of jobs on each of the rows, they become either DEGs or SEGs, depending on which you're using.
Great, thank you. And I think this discussion actually addressed a similar question. How does the narrative of similar exposure groups fit into the DEG and GEM discussion? And are these terminologies implying similar things?
I think they can be, would be my answer, just to remember when you're reading papers or deciding what term to, I mean, DEG is just something we made up. So like, it's not like a thing, but similar exposure groups are kind of jargon that people think they know what it is. So if you read it, they think it means one thing. So just make sure you read carefully. And if you're writing, that you clarify what exactly you've done.
Thank you. We have another question. What one element, if you had to choose one, an IH data collection would be most beneficial for epidemiology studies? Job title, task?
I don't know that I could go with one element. If they mean in terms of the identification.
Maybe they could clarify.
Yeah,
sure.
I think I would ask the questioner to be clearer. Do you mean from the list of information that needs to be associated with any sampling result, or do you mean, are you asking the choice between job title or task? I'm not quite sure.
Great, we'll give them a moment if they want to respond and clarify a little bit more. We had another question, if you could also just take a little time to, more specifically, how long did it take to create the DEGs for the AMC study?
Well, what's a little unfair is that I was not involved in the creating. They actually, and Kathy, I don't think you were either, were you?
No, I was not involved in the SCs, but I would also say this was an ongoing process.
Yeah, that's true too.
Like many things that happen, you know, you get 80% of the work done with 20% of the effort, you know, the 80-20 rule. And then doing that, the next 10% takes 50% of the effort. And,
absolutely true.
And it's asymptotic. You know, there just comes a time you simply say, we can't go any longer. And that's often driven pragmatically by just what resources you have available to do it. But having said that, I would say that a team of people came up with the original ways of trying to group the jobs. And the grouping was intended to be able to match the industrial hygiene job titles with the human resources job titles. I think that the team of people was composed, probably the core was about 4 people, and then various other people were brought in at different times. And they worked over a period of years in doing it. But the very first one was probably developed in the space of about 6 months. Probably, you know, each of them working between 10% and 25% time on that task.
Yeah, and I mean, in a data set like we had with AMC, you expect it to evolve as you get to know the data better and as it moves forward. And so, for example, in the presentation today, I talked about 294 DEGs, but actually by the time we got around to later analyses, we'd moved up to 310 DEGs or something, and a whole lot more people because they've been able to clean more HR data. So, you know, it's things like that, in the best case scenario, really, you have an ongoing relationship with your data and you can do more things with it as time goes on. Looks like we have a clarification.
Yes, we did have a clarification come in. From an information collection in the process of assessment, what is the most useful for future review by EPI? What can I do as a field IH to make your analysis easier, better, more useful?
I think that is what it's slide
Oh yeah.
59 in our talk. And if it, basically make sure that each sample has this type of information. You know, it clarifies if it's a random sample or if it was done for a different reason, if it's a personal sample, you know, where the job was taken or the job title of the person doing it, the duration of the sample. And you know, sometimes you get results that are all less than detectable for all the samples, like beryllium samples sometimes, or radiation samples. And it's really important to know what that limit of detection is, because in some cases, I know that in radiation sampling, many places have labeled things less than detectable if they're less than the standard, even if they had a numerical value. So they were detectable, but they were listed as LDs.
That's
So
frightening.
it's very important to know that kind of information, because most of my research is looking, the reason we're doing epidemiology studies is to see if there are health effects below the existing standards. And so a thing that is just really saying it's less than the standard is less informative. But anyhow, having this type of information, also whether respirators were used or not, or any other circumstance, there should almost always be a comment area. Having a standardized data collection sheet that has this information and keeping those data together with the result is very useful. The measurement methods and sampling methods too.
I would say that having it standardized probably makes your life easier in collection of this information, and makes our lives easier later, because you've probably gone through and filled things out. You know, you notice where, oh gosh, we all know this. You go out in the field to sample, and I am an enormous vocal proponent that everybody read the SOP, that you know what's going to happen, because once you're out there doing it, you get caught up in the moment. And so you want to have your method. And the same is true for taking down information and having a good log sheet, and then having a good method to transfer it to, you know, most people probably these days transfer it to an Excel spreadsheet or some other type of specialized database. And so that helps you and helps us to like always have the same, like Kathy says, list of information, and a comment section. You know, if you want to note like, well, this was a personal sample, but other employees reported that they saw this guy dragging the sample across the floor multiple times during the day. You know, things that I've actually seen in comment sections. And so, you know, I think, yeah, standardized basic information like on this slide is what makes everybody's life easier.
Great. Well, thank you both so much for this presentation. Thank you, Dr. Hammond and Dr. Noth, as well as everyone who joined us for today's webinar. The Education and Research Center Industrial Hygiene webinar series will take place the second Tuesday of every month. The series is in addition to our ERC ergonomics series, which takes place the third Wednesday of each month. We'll be taking a brief pause in July, and our next industrial hygiene webinar will be on August 11th with Dr. Brian Pavlonis on nail salon exposure assessment in partner with New York, New Jersey Occupational Safety and Health Center. Be sure to check out our website for more information and to register for upcoming events at coeh.berkeley.edu/about-CE. Thank you again, and as a reminder, you will receive an email at 12 p.m. Pacific tomorrow with a link to the presentation and also to the evaluation to be eligible for your certificate of completion. Thank you all so much again. Have a great day.